purely by chance on the internet. Got to this guy's website. He had a board for sale on eBay and a bill of materials for eBay France, and I started to look up each of the component parts. It's very modular, and found that the parts were available on US eBay, all of them. Others I had in my collection of parts. So I said, hey, I started looking at the pricing of it with the board and the individual components. It uses an Arduino Nano as the main microcontroller for it, which is not that old, but a little bit more obscure than a lot of the other Arduino or Arduino clones that are out there. But that was a microcontroller that's still available. So all the parts are available out there. Didn't have any problem, sourcing any of it, and nothing really very exotic on it at all. So, as I said earlier, I think the PCB minus the shipping runs about $6.80, so it's pretty inexpensive. With the postage, I have been in contact with Tony, so we can do just a one-time order of all the PCBs for those interested in starting it with the build-a-thon. As you'll see after I go through the little demo here, we'll pass it around or you can come up and look at it. It's a fairly compact unit. It's centered around the Nano and the Analog Devices 9851 DDS modules that you can get on eBay, and you can source those from numbers of places in the U.S. and China. And that was the other thing. Everything I got, I was able to get from U.S. sources in relatively quick 3 or 4 days off eBay. So there really wasn't anything that I had to get from overseas other than the PCB itself from Tony in France. There's one bidirectional coupler that you're winding through a binocular toroid, a fairly large one, but one that's readily available. And then a kind of more obscure relay, but I happened to get a bag of them from Electronic Gold Mine. It happened to be the exact right relay. So I have more of those. Certainly I have enough of those and the binocular toroids and one other thing. Oh, and the PCB mounted connectors in both SMA and SMB. So, certainly willing to part with those components as well. Probably one of the most expensive parts other than the Nano is the display, because it is a 4-line display. I don't use it standalone typically, but it'll run as a signal generator standalone, and it'll run as an SWR meter, if you will, standalone. So you can hook it up to antennas, get a whole range of information on them. But I use the software that I'm going to show you called VNAJ, which is a Java application that was written for the Mini-VNA line. So that Mini-VNA line started some years ago and has expanded to, 6 or 8 different models now at all different price ranges, frequency ranges. They have them up to 3 gigahertz now. The Mini-VNA started up to go up to 180 megahertz from 100 kilohertz. This particular design goes from 1 megahertz up to 60 megahertz, okay? So it's a limited range, but of course it's a pretty minimal cost point too. There are options to extend the frequency range, but basically for typical HF work, you've got more than enough there for our use. Now what you do after you put this together, he's got it set up like a typical kit. He's got 1 page of instructions on his website, and I had sent you guys a pointer to that after, I think, the last meeting. That's it for instructions on the build. It's pretty self-explanatory if you look at the schematic, because it is so modular. Most of what you're doing, other than the toroid and the relay and a couple of chips is soldering headers and sockets on to plug the other components into, okay? As well as header jacks for wiring going up to the display or to the rotary encoder in the front. And the flash module, probably the one thing I didn't like about the design is it uses a removable micro SD flash to hold the calibration constants, which we'll talk about in a second. He could have used a flash chip, but it would have been less money overall and much more convenient, because then you don't really have a reason to ever take that card out and put it in another unit, when you can simply just copy paste them from computer to computer. And really, as it turns out, and I'll show you, you should recalibrate this every time you put it on another PC for a variety of reasons. But this is actually a sensitive enough device that it will pick up losses in as little cable as 2 of these put together. Okay, so it knows the difference once you've got it calibrated for transmission loss. So you can measure transmission loss or reflectivity. I use just a little jumper here. This is just something I pulled out of a parts unit that's just some RG141 semi-rigid with a couple SMA connectors on it, and put that across both the device under test port and the detector port on the VNA. And then you also calibrate it with an open, which is just as it sits. Once you've got that calibrated and you've done the frequency count calibration, then you're set to go. Now, the frequency calibration without a frequency counter, he gives you a starting point. So essentially what you're doing is you're entering in a number as a divider for that DDS module in there. So he gives you the starting point. It was only off 0.2 of a hertz when I put that number in. So when I dialed it in from there, it was just, for giggles, basically, just to do it, right? So you really don't need a frequency counter, right? But for the build-a-thon, if it looks like something that we can get done within the time span of the build-a-thon, which I think you can. I mean, this essentially, with all the parts in front of you, is a couple-hour project. I'll have one of my frequency counters here in case you want to do the alignments. So let's do a quick test here. If I put a 50 ohm load on, this is just a little mini circuits SMA type 50 ohm load. And then I run a reflection test. And what it's going to do is it's going to go through and do a scan. As you saw, it's fairly quick. Now let's do it from 1 megahertz. Okay, so the start and stop frequencies are specified in hertz. And we'll go up to 30. Oops. Okay, so what that shows us is it shows us the return loss in decibel. So right here is going to be where our best standing wave ratio is going to be, because that's where the least loss is seen reflected back. If I put SWR on there with the blue trace, then it's down here, and we're essentially under 1.02, 1.06 to 1 across, which is what you'd expect with a 50 ohm resistive load. We can also show the impedance, and if we take auto scale off, as we'd expect, it's flat across, but auto scale actually brings it in so we can see some deviation. So you can see that this load is real close to 50 ohms until we start to get up in frequency a bit, and then it starts to trail off slightly, but not very much. I mean, we're at 50 there, back here we're at 50.6. So obviously, even at the highest frequency, we're still, looking good from a load standpoint. It'll do Smith charts. So if we pull up the Smith chart, we see that we started off into here and got right to 50 ohms, and that simply is represented by the spike here because of starting at 1. If I make it slightly higher than 1 megahertz and not an even frequency, then it gets rid of that. That's just a little bit of a quirk with the software. But we'll show a little bit more complicated example. So let's say we had a filter that we wanted to characterize, and there's a couple of different ways we might want to characterize it. We might want to see what the loss response looks like, the curve, the 3 dB point, the 6 dB point, and such. We also might want to do something that we normally can't do very easily. We might want to look at the characteristic impedance over the frequency range, especially if we're putting that filter in on a transmission line at the output. So not a filter in circuit in a low power situation, but a higher power situation to see what the characteristic impedance might look like. So here I have a low pass filter that I inherited when I bought a bunch of these Pomona boxes off of eBay that some presumably ham did, because all the frequencies are ham bands. And we'll run it up to about 6 megahertz, starting at 1 megahertz. Now, I happen to know from the labeling on the filter that it's essentially a 160 meter filter, right? So we're going to be at 1.8 megahertz. So we'll start at 1, we'll go up to 6, and we'll look at the reflection measurements on it. And so what we see on the return loss side of things is kind of what we'd expect, is at the lower frequencies we have a lower loss, or essentially a better passband through, and then we drop off. And we drop off fairly steeply, okay? If we run the transmission side of this, we'll come back to the reflection in a minute. Then we see the characteristic curve we'd expect, which at near 1.8 megahertz or so, we're really only losing about a dB or so through the network. But then as we go up higher in frequency, we start to see, we get even here to out of the ham bands into about 4.8, 4.5 megahertz, we're down 40 dB, which is great. That's a pretty good filter.
What's the blue again?
The blue is the right side, and the green is left side. So there's two scales, left and right, that you have. So the left range is over here underneath the green, and the blue sets the right range. And for transmission, the only really useful thing other than theta is the phase. So, for example, as going through this network, it's going to shift up to 180 degrees as we kind of expect at a point, or at least 90, and then go back towards 0 degrees, and then back to 180 over a broader frequency range. We can also take that off by selecting none and just put that in. There's a bunch of export options to export S parameters, export to Excel, export to XML, which is handy for importing into other drawing programs, and then exporting to a particular drawing program called Z-Plots, which I didn't really care for, but it's there. That's so you can get this whole thing exported and printed, or exported into a GIF, which it does, and then put on a blog post or whatever you want to do with it, or in your log, your workbook. So if we go back to reflection here for a second, show you another kind of cool feature of this. So let's go back to here. All right, so we have what we kind of would expect from a return loss standpoint, but you'll notice the blue line now is my characteristic impedance. And I'm actually getting up to about 108 ohms, 109 ohms of impedance, right? Now that would be real and imaginary combined. And then coming down to something as low as 6.2 ohms of characteristic impedance. And that's not unusual through filters. You know, if you get them set up in circuit at 50 ohms, and make them narrowband enough so that 50 ohms is essentially where they stay through the operating range, then you're fine. But realistically, if you don't try very hard, it's going to do something like this. Its characteristic impedance is going to go all over the place. And that's why I said earlier, if you were trying to make a low-pass filter for transmission use, then you want to be careful that you're not going to get to a super high SWR, or that you aren't going to have to actually tune the low-pass filter out in terms of a match. So I don't have one with me or have one that I've made or anything, but you would typically, from the operating range you're looking at of interest, let's say in this case 160 meters, 1.8 megahertz, you'd be looking for a relatively low SWR, of course, right through that filter. Beyond that, you don't care, because the harmonics are going to see SWRs of 10, 20, 30 to 1. That's what you want. You want those all attenuated out. One of the cool things there's actually a number of cool things this does, but if we look at the return loss here, and we look for the lowest point, minus 21, and we go up, let's see, to 18, kind of doing this backwards, but you'll see in a minute what I'm doing. So we can set a marker just with a click, or shift click, or control click. And so there's the 3 dB point that's set. That's close enough. There's the 6 dB point. If we go back to transmission for a second, over that same range, those markers will stay there, and we should roughly see the same kind of results, which we're not. Let's see. Let's make sure I got my cals loaded. All right. So let's do that again. Let's find a 3 dB point. Let's find the 6 dB point. Okay, when we go to look at reflection then, we've got our points there. So the excursion that we're taking between the origin and the 3 and 6 dB points are on our markers here on the Smith chart view. And so we're sitting at 53 ohms at the 3 dB point, and we're sitting at 89 ohms at the 6 dB point. SWR has popped up to 4.3. Here it's, 4.3 on 0.1 and 8.5 at 0.2. And at the origin, we're pretty close. Not too bad. Yeah. So we get down to about 57 ohms is what we see. So it starts to climb up. It doesn't get too bad up here at the high end of the 160 meter band, but high enough. It's not a great filter. It has a very sharp roll off, but it's not very good from as an output filter would be. Okay, so the other thing I wanted to show you then.
Do you have any means of controlling the amplitude of the signal at the output jack?
No.
That's fixed.
It's normalized, yeah. It's set up as part of the setup of this. you really don't worry about that. That's one step of the setup. But one thing you do have to do is, and I got lucky as it turned out, but when you put on the little surface mount resistors for the load for the bidirectional coupler, they're going to be 49.9 ohms, standard value, 1%. And then he allowed 2 parallel resistors to bring that in range. So if you used a 51 ohm and then you wanted to parallel that with 100 or 470 or something like that, you could bring it down closer to 50 to tweak it. But the 49.9s that I used were so close to 50 that I didn't have to do any of that.
How much power does it actually put into the drive side?
About a milliwatt.
So
Yeah.
if you wanted to do an active device, like a broadband amp,
Right.
it's going to throw that in there unless you put in a attenuator and then adjust your thinking.
Absolutely correct. Absolutely correct. Right. So, good point. I had built using a mini circuits MMIC, a little broadband amp, and had to attenuate the input a bit to account for that. So I put a 10 dB pad in there, got it in range where it needed to be, so that coming back through the detector, it was within reason. Right. It wasn't overbearing, especially. Right. So attenuators play a very important role in these vector network analyzers. It was one of the questions I had because I had saw people talking about using attenuation for VNAs, but never really understood why you might put a 1 dB pad or a 3 dB pad or a 10 or a 20. I could kind of see, but why you would put these smaller pads. And for a very expensive unit, that's part of the calibration and part of the device under test and specific to what you're testing that you'll use them. For a 4-port analysis with all the S parameters coming directly back, then you're going to actually have a calibration set, and they typically come in little wooden boxes, and you pay funds of money to get these calibrations. So you got a short, a load, and an open, and one other one, and essentially the what? Through, right. And essentially what you're doing in buying these is to get the calibration constants that you can load into the big Agilent or what have you vector network analyzer. So that's why there's so much money, is because they're individually characterized by hand. All those numbers are written down for you, and you enter those numbers in when you run through your calibration steps. With this, it's a 2-port device, and it's a much easier setup. It's better than a scalar network analyzer because you do get the phase, and then you can get complex impedances and get a Smith chart and all that. It derives the scattering parameters, the S parameters, but it's a $70 piece of equipment, right? So for what it costs, it's pretty impressive in terms of the results that you get back from it. It does a nice job from an attenuation and power level perspective. Let me just show something here quick. So if we look at transmission loss through just a length of cable over a fairly small range, and we don't see too much from a transmission loss perspective. It's sitting at 0 dB, occasionally pops to minus 0.06. That's within air of an instrument like this. So essentially sitting flat across the range. If I put an attenuator in the middle of it, then a good test for an instrument of this caliber is if I have a known attenuator that I've characterized with much better equipment, which this is, and it's come with a certificate of calibration, which this did, then I have a measurement, not so much a transfer standard, but I have something to compare against. And actually this comes very close to where it should if you had spent a great deal more money. Add 4 or 5 more zeros to what something like this cost to get a VNA. So this is actually a Mini Circuits 3 dB pad. These work and are really more intended for gigahertz or multi-gigahertz purposes. But it comes pretty darn close. It's actually sitting at minus 2.82, which again for a device like this is within reasonable error amount. It should be minus 3. When I put it on my reference source and use my HP 467 power analyzer across this range of frequencies, then I see pretty much 298 to minus 3 dB of attenuation. So you see what you'd expect to see, and that's what the data sheet said that it would do. And on this, you see something roughly the same. Is that a coincidence? Well, yeah, it could be a coincidence. It could be a lucky coincidence that happened to come out that close. But I have a set of attenuators and some other things that I've had characterized, and they all track really good. So, for $70, I mean, it's a nice device. It's a fun little kit to put together. Doesn't come with a case. That's also a good thing, though, too. You can customize your own enclosure for it. I looked at purchasing enclosures, and not a lot out there. The length of the PCB is great from an enclosure standpoint because it's a good length. It was engineered with that in mind. However, you have to pretty much go with something like SMB connectors on the output and not the screw-type SMAs that I have right now. It'll accommodate anything of that size, SMB, SMA, in terms of right-angle connectors. So I bought some right-angle SMBs that I got a good deal on, and so I would recommend you use that if you're going to have it in an actual enclosed case, and then you're just snapping the cable connections on. But it depends on what you have for cables and how you're going to use this, and how much you're going to be doing it in BNC and all the rest of it, right? So, all right. I'm sure you might have some questions, or I've completely lost you and confused you.
Does it do group velocity too?
Sorry?
Will it do group velocity phase? In other words, you get a phase rolling with frequency?
You can figure out group delay through filters and stuff, yeah. And you can see delay through coax.
Yeah, I mean, you get this, every 360 degrees, certainly at these frequencies, it may not be that useful.
Right.
It's not going to get much going on, but you get in the gigahertz area, it tells you a whole lot, just by glancing at the screen,
Right.
how well it's tracking.
Yeah.
On the phase side.
Yeah. I don't think, although, the delay is in there, the theta GR, the group is in there. I haven't looked up to see what regular theta is even, and I haven't cared, I guess. If I don't know what it is, I guess I haven't cared enough yet to figure out what it is. But the group delay and all that's kind of handy to have. I haven't verified that yet. There are some known ways that you can measure things like that, that aren't lab standards, of course, again, but just to kind of see, is it close enough? Anybody else? Yeah, well, feel free to come up here and check it out. A little more meaningful to see it firsthand, I think. It has a 5-volt power input, so that could be any number of volts stepped down to 5. So that's the main primary power. It does power from the USB connection for the command side. But it doesn't really have enough oomph to get the backlighting on the display. So I essentially just made a USB connection here to go for the 5 volts. I originally had put in a step down from 9 to 5, but I thought, I don't have to fit it in here, why bother with it? It may have dimmed slightly, but that's all it does is dim slightly until you actually run it.
So, if we were to want to go with this, right, we need to circuit boards from France,
Yep.
and the rest of the parts can be sourced domestic.
Right, and what I would do is, as I've done before in the builds, is I would source them. So if we were gonna build 6 kits, let's say, then I would get 6 of everything or what have you. Like I say, some of the stuff I already have, but other things I don't have. So I'd have to go and get another synthesizer module, 1 each for those, 1 nano each, a couple of different things, and leave it up to you guys whether we wanna do a bulk order or you guys wanna do it yourselves, either or.
And the price is in the neighborhood of $70.
Right. Right. So what I have almost done, but not quite, is I have the full bill of materials, and I was putting the current prices on eBay and DigiKey in for each of the parts. I have to finish that up. I'll distribute that out, and then we can make a decision on how many we have. The way I feel about it is if we got 2 people that are really interested seriously in putting it together, then I think you could go get your own parts. They're not really going to gain anything. But if 8 of you want to put it together, then that's a different deal. Then I can get the circuit boards directly through Tony. I don't have to go through eBay France, which was an interesting experience in and of itself. And go through the exchange rates and all of that and just get them directly from Tony then. So I'm willing to do that if enough people are interested in it. In fact, I'm willing to get the boards anyway, because there's no reason that all of us for a one-time buy who are interested in building it should go and register on eBay France when you're just going to make one purchase. I mean, it just doesn't make a lot of sense.
Shipping for 10 boards is the same as the shipping for one.
Pretty much, right, pretty much, yeah. And I think that was about $13 US. So that was one of the reasons I had contacted them, because exactly what you said, if it's $13.50 to ship 6 of those boards rather than 1, for 50 cents less, then we might as well do that. So. I could hear a pin drop.
What was the frequency range?
It varies by the synthesizer and when you're done building it, but right around 1 megahertz and then up to 60 megahertz. The limiting factor is the DDS. This particular DDS that he sourced is only good really up to 60 megahertz. There are other ones that you could put in, and how close you get to this footprint starts to get you into full-on hacking to get it to fit. But there certainly are DDSs that go into several hundred megahertz. They just have a completely different footprint than this module did. It's higher than the 9850, the previous generation that a lot of people bought out there to interface with an Arduino. That had worse characteristics. It had spurs. It had all kind of problems with it. The 9851, another 10 megahertz out of, and it leaves a lot of the spurs and noise behind. So it was a good move, but he put this together, I think, 2 years, so this design's a couple years old now. Certainly if someone wanted to try to do one today without the module and maybe putting a better DDS directly on the board, you could probably get up into UHF range, I would think, pretty reasonably. So, but you have other problems when you do that, right? You have to use read relays past a certain point in the frequency range, and you have to think more about shielding, and some other things will bite you as you get up in frequency, of course. So
How about stretching the low end of the
down.
frequency range, yeah. If you wanted to hit like a standard radio IF 455.
Yeah, it'll do 455 without a problem. Yeah. It's just that to get down to the 100 kilohertz where the Mini-VNA starts, where you're flat, isn't going to happen, right? So you're only, when someone asks me what the range is, I'm interpreting that question as where you flat, right? Where you 0 dB across that range. And you can get to 455. You can get to 472 kilohertz if somebody were interested in 630 meter stuff or anything like that. You can hit it, but this DDS is starting to get pushed a little bit, and its power output really isn't adequate down at that low frequency range
So
really
you
either.
wouldn't want to try it at 190
Yeah, I don't think.
HRO juniors.
Well, what happens if you look at sawed across there, it sort of goes wild, and then it comes back to where it should be, and it's flat, and then it goes wild, and then it's flat. I mean, if you happen to hit a flat spot, then you're fine, right, for all intents and purposes. So,
The software is free or?
yeah, the VNA-J, thank you. There's only one driver, and that's a USB driver because it uses a different USB driver, the CH340, than a lot of what's out there today. So it's a little bit older driver, but that's free, and Tony has the link on his website for that. And then this VNA-J, he has the website link for as well. This is version 3.1.14. I think when I first put this together, it was 3.1.12 or 13. So it's changed a little bit since I put it together, but that's still actively kept up to date. As I said, that got adopted for the whole the Mini-VNA line, the commercial line, and the guy that did the software gets a royalty from the sales of the Mini-VNA unit. So that's what's funding him to keep up the software. But for everybody else, it's free. So that was kind of what Tony was capitalizing on, is if I could build something that looks like a Mini-VNA, then the software's free. That's what he did, essentially.
What's the potentiometer on the front there?
Oh, this is actually a rotary encoder. So when you first power it up, if you hold the switch down on power up, it'll go to the front menu. And then you have 4 choices. The fourth is calibration, but the first 3 are frequency signal generator and SWR standalone, and then the VNA-J mode, which is mode 3, the mode we're in currently, to work with the software.
Cool.
So if you use it standalone, I have the cable essentially harnessed in here, but if you were going to use it standalone, all you need is that 5-volt source in the back. You need a way to power this, and then use your cable adapters to your UHF connector or BNC connector, and then you can characterize your antenna standalone here. And because I didn't have a particularly great way to project that, I couldn't show it, but the screen's actually got quite a bit of information in it. It shows the characteristic impedance, it shows the phase, and it shows the SWR. It's got quite a bit of information on it, so you can actually see quite a bit by doing that. And you actually set the start and the stop frequency on here, so there's a way to dial that in. So you can hit one frequency on a piece of coax, or you can hit a range, all standalone without the software. Yeah, so that's nice.
Does the calibration cycle require calibrated wrenches?
Calib-
Down, I know an SMB you wouldn't have that, but, SMA would torque it to, I don't know, 8.5 pounds or something.
Yeah, I have a wrench, and I hadn't found that at these frequencies it made any difference, right? But I know why you're asking that. It's not critical, and that's again why I would suggest having the SMBs just a plug and unplug, because the duty cycle, even though that center conductor is so fragile, the alignment's good enough that I think plugging and unplugging is you're pretty much where BNC is over a long haul. SMA, I can see myself on soldering these at some point and replacing them, right? Or you essentially put SMA to BNC connectors on and just leave the BNCs there and just use BNC cables, right?
It's tough on your connector.
Yeah. I mean, that's the thing about connectors, it's what cracks me up about the mini USB and the micro USB in particular, is those things were never made for the number of plug cycles that cell phones have. They were never spec'd, past like 100 plug-unplug cycles, and everybody goes past 100 cycles, right? And then all of a sudden they're starting to fall out of your phone,
In
right?
the first 100 days, they own the phone, yeah.
Yeah.
Every night, right?
Yeah, well, USB-C is going to fix that. Anyway, any other questions? Okay, well, feel free to come up here, check it out.